Continuing with our series on axial rods in tension or compression, now we're going to discuss a problem similar to the ones we started at first, which was a prismatic bar subject to tension, but in this case, the axial load, it's not an external load acting at the tip, but the distributed self-weight of the bar. So if you pick any point, X, from the tip, you will find that that differential slice, which we can think of a rod in an infinite link of rods in series, that one is subjected to a weight which is equal to the weight of the rod that's underneath that section. So in this case, since the rod has uniform area, it would be A times rho, which is the density, times G, gravitational acceleration, times this length here, X. So that's the load, P of X. And that load changes as a function of X, right? As you go higher, the total load acting on the corresponding slice of the rod, it's growing. So using our fundamental formula, we can find the vertical deflection as the integral of the total deformation of each one of these infinitesimal slides that make up the whole rod. And since there are infinite number of them, we have to use an integral. So P times the length, which is dx, divided by A, divided by E. If A is constant and E is constant, then these can come out of the integral, right? And we are left with this expression, 1 over AE times the integral from 0 to L of A rho G X dx. A is constant, rho is constant, G is constant, so those can also be taken out of the integral. The A's cancel, and we are left with rho G divided by E times the integral from 0 to L of X dx. From basic calculus, we know that this integral is going to be equal to L squared over 2, right? The integral of X, X squared over 2, substitute 0 to L, and we get our result that the total deformation, rho G times L squared over 2E. To make this result a little bit more intuitive, we are going to multiply and divide by A. It's basically multiplying by 1. But what this does is that it transforms this result into something that we can get some intuition from. Basically breaking up this L squared into an L here and an L out here and bring the two this way. And so we can see that this multiplication here is simply the total weight of the rod. Area, cross-sectional area times rho times G times L. A times L is the volume, rho times G is the specific weight per unit volume. And so our expression becomes the weight of the rod times L divided by 2AE. If you compare that expression with one of our first results, right, which is if you have a bar with a load at the end and the rod is prismatic and has an area A, modulus elasticity E, and a length L, the deformation here is PL over AE. So comparing these two, we basically can conclude that the deformation of a rod in tension due to its own weight, it's going to be half of the deflection that would have occurred if the whole weight of the rod was applied as a concentrated load at the tip. This is an important realization because it illustrates, in a very simple case, nevertheless, it illustrates that when you apply loads that are distributed as opposed to concentrated, the deformation effects can be significantly different. In this case, the deformation is 50% of the deformation that would have occurred if the same weight would have been applied concentrated at one end. So this is an important problem that illustrates that phenomenon. Again, the general idea is that distributed loads create significantly different deformation effects, even though their static force effect is the same, right? Because here, the reaction is W, right? The weight of the bar. Here, the reaction is P. So even though the reactions are the same in the sense that, the static effect is just the reaction due to the total weight, the deformation effect is completely different.